Hello students, this is Dr. Anita Raj, your chemistry mentor, welcoming you for one more session coordination compounds. Today we shall see the different types of stereoisomers like geometrical isomerism and optical isomerism involved in coordination compounds, right? First let us see what is stereoisomerism. See, stereoisomerism, in this type of isomerism, different atoms or group of atoms occupy different spatial positions or different spatial arrangements around the central metal atom. Okay, so the different groups of atoms will be occupying the different spatial positions around the central metal atom. So the isomers thus obtained are called stereoisomers. Understood? So these stereoisomers are of two types. For the first one is geometrical isomerism and the second one is the optical isomerism. So what do you mean by geometrical isomerism? Actually, this arises due to the different spatial arrangements of groups around the central metal atom. So different spatial arrangements will be there, okay, of atoms, right? Then optical isomerism. Actually, this type of isomerism is seen in complexes whose molecules are asymmetric. Okay, see what do you mean by asymmetric? That means a chiral center. So the groups will be different. Okay, so the complexes whose molecules are asymmetric exhibit optical isomerism. Understood, students? So let us see the geometrical isomerism in detail now. See, this geometrical isomerism depends upon the coordination number of the central metal atom and also the geometry of the complex. What do you mean by coordination number? It's the number of atoms or groups or ions or molecules attached to the central metal atom. Okay, so this geometrical isomerism depends upon the coordination number of the central metal atom and also the geometry of the complex. Okay, so next we are going to see the types of geometrical isomerism now. So there are two types of geometrical isomerism, that is cis isomer and the trans isomer. When the cis isomer occurs, so when similar groups are arranged on the same side of the central atom, we get cis isomer. Understood? So we could see the similar group, same type of groups will be arranged on the same sides of the central metal atom on one side or this side or this side. Okay. So and next, what is trans isomer? When the similar groups are arranged on the opposite side of the central atom, we get trans isomer. Understood? So when these similar groups are arranged on the opposite side of the central metal atom, we get this trans isomer. Understood, students? See, actually, this geometrical isomerism can be seen in the 4 coordination compounds as well as in the 6 coordination compounds. Okay. See, in 4 coordination compounds, these compounds with coordination number 4 are either tetrahedral or square planar in shape. See, the compounds with coordination number 4, we can have the structure either tetrahedral or square planar. Okay. But these tetrahedral complexes cannot show geometrical isomerism because all the 4 ligands lie at the same distance from the central metal atom. Understood? See, if this is the central metal atom, all the 4 ligands will be from the of the same distance from the central metal atom. In that case, a tetrahedral complex cannot show a geometrical isomerism. That's why, but this geometrical isomerism is very common in the square planar structures. Understood? So we are going to see the different square planar complexes which exhibit this geometrical isomerism. So the first one is the complexes of the type M, A2, B2, N plus or minus, where this M represents the central metal atom and A represents a ligand and B also represents the ligand. So the first type is the complexes of the type N, A2, B2, N plus or minus. Okay. So I have taken an example. Let me write the example: PT, platinum, then chloride, chlorido, okay, NH3, NH3 means amino group, okay. So this is the compound, okay. So now this compound can exhibit both cis as well as trans isomer. See this cis isomer, this is the cis isomer. See here, this platinum is at the center, that is the central metal atom at the center, and this is obtained when both the groups A and B, both the groups A and B occupy the neighboring position. See here, chlorine, Cl2 or Cl represents A and NH represents B. Okay, see this A as well as B both are occupying the neighboring position in cis isomer. Understood? So in cis isomer, both the ligands, okay, the same type of ligands are on the neighboring, okay, position. So that time we'll be getting the cis isomer. While in transform is obtained when the similar groups, when the similar groups occupy the opposite position or the trans position around the central atom. See here the similar groups are occupying the trans position around the central atom. So this is the trans isomer. Next we shall see the next type of complex which exhibit this geometrical isomerism, complexes of the type Ma2BCN plus or minus. Okay, see here it is Ma2B2, but here it is Ma2BC. Okay, so three types of ligands are there. Understood? So in this case, the cis isomer is obtained when the similar groups are that is similar groups A are adjacent to each other. Okay, so here the similar groups, these are the similar groups. So let me take an example for this. I'll give an example for this: PT, Br, Cl, NH3 twice. Okay, so this compound is an example of this one where PT represents M, platinum. Okay, A2 is nothing but NH3 twice. Okay, B, it is Br, C, it is Cl. Understood? So this is the example for this type. See, in the cis isomer, the similar groups are present in the neighboring position. Okay, that is A, the ligand A2 is present in the neighboring position. Whereas in the trans form, the similar groups are placed in opposite position. Did you see here? Okay, so the similar groups are placed in the opposite position. Okay, so this is the second category. Understood? So the next type of complexes of the type MABCD. Okay, N plus or minus. Understood? See, when all the four, this M represents the central metal atom and A, B, C, D represents the different ligands. So all the four ligands are different. Is it not? See here, this is an example. Let me write the example now. We'll give you an example now. This platinum, this is the central metal atom. Br, this is one ligand. Cl, this is another ligand. NH3, okay, this is another ligand. And pyridine is another ligand. So the central metal atom M is attached to four different types of ligands. Okay, so when all the four ligands are different, then three geometrical isomers are possible in square planar. Okay, so this is a square planar structure. So in square planar structure, when all the four ligands are different, we will be getting three different types of isomers. Understood? So this is the case. Okay, see pyridine, bromine, chloride, and amine group. Here also the same. So we will be getting three different types of geometrical isomers possible. Okay. So the next category is the complexes of the type MAB2N plus or minus. Okay. So in this case, this M is the central metal atom, while AB is an unsymmetrical bidentate ligand. Bidentate means the ligand will be attached to the central metal atom through two donor atoms. Understood? So when two donor atoms are present in a ligand, then we call that as bidentate ligand. Okay. So this AB is a unsymmetrical bidentate ligand. Okay. So if a complex contains an unsymmetrical bidentate ligand, then it is attached to a central metal atom, then we can expect this two type of isomers, right? So an example of this type of complex is platinum GLY twice. Okay, where this GLY is nothing but it is glycino. Glycino is nothing but NH2 CH2 COO minus. Okay, glycino. So this is a ligand. Okay, so this can attach this. This is a ligand, and this can attach through this nitrogen as well as through this oxygen. Okay, two donor atoms are there, so it is called as a bidentate ligand. So this can give both cis as well as trans isomers as shown in the figure. See here, in this case, this nitrogen is attached to this platinum and oxygen is attached. Here also nitrogen and oxygen. But in the trans isomer, the position has changed. Did you see? Here O and here NH2. Just the reverse. Okay. So this is cis isomer and the trans isomer. Understood, students? Next comes the 6 coordination compounds. Okay, the coordination compound containing coordination number 6. Okay, so the complexes with coordination number 6 are octahedral in shape. So normally a regular octahedron contains 8 faces. Okay, it will be having 8 faces and 6 equivalent vertices. Understood? So in an octahedral complex, the metal is placed at the center. okay, and 6 ligands occupies the vertices, okay. So the 6 ligands will be placed in the vertices, okay. So here also we are having certain types. The first one, first one is the complexes of the type MA4 B2 N plus or minus, okay. So this category in this complexes 4 monodentate ligands A is there. Is it not 4? 4 monodentate ligands A and 2 monodentate ligands B are octahedrally attached to the central metal atom M, okay. So actually what happens is in this type the cis isomer is obtained when the ligand, or that is the monodentate ligand B, occupies the adjacent position 1 and 2. When B occupies the adjacent position 1 and 2, and trans isomer will be obtained when when this B ligand occupies the opposite position, okay, just opposite to each other, then we'll be getting that. Explained with an example now. So let me take an example: cobalt Cl2 NH3 4 times. Okay. See here, this is let me take, this is ligand B and this is ligand A. Okay. As I told you earlier, the cis isomer and the transforms of this complex cations are shown in this figure. The in cis isomer, the 2Cl, okay, the 2Cl atoms or ions are at adjacent position. They are in the adjacent position. Did you see? And hence it is designated as a cis isomer. Whereas in trans isomer, the 2Cl are in opposite positions. That is in the first and the sixth position. Okay. So that's why, and it is designated as the trans isomer. Understood? That's why it's designated as trans isomer. Understood, students? So the next complex type is complexes of the type Ma3B3 N plus or minus. Okay, Ma3, where M represents the central metal atom, A is one ligand and another B is another ligand, and we are having 3 times, right? So let me give an example for this category. Chromium Cl3. So A is Cl3 and NH3 thrice. NH3 is B. Okay. Now see here in the cis isomer, here also we are having cis as well as trans isomers, is it not? So in cis isomer, the 3Cl ions, okay, so the 3Cl are placed in a triangular, okay, in a triangular phase. See here, this is a triangle, and in this triangular phase we are having the 3Cls, okay, and the NH3 molecules are just placed opposite to this triangular faces. So just opposite to this triangular faces. See, this NH3 is placed just opposite to this, okay, and this NH3 is placed just opposite to this, and this NH3 is placed just opposite to this. Understood? So this is called as a facial or a FAC isomer. Facial, okay, FACIAL, facial isomer. Understood? Whereas in the case of trans isomers, the Cls are placed in the edges of the octahedral. Okay, this is the octahedron, is it not? So along the edges we are having the chloride ion, whereas the ammonia molecules are just placed opposite to the edges. Okay, see here, so just opposite to this Cl we are having one NH3. Opposite to this we are having one NH3. Okay, so like just opposite. See here, NH3. Okay, NH3. Just opposite to Cl, we will be having NH3 molecules. So this isomer is termed as meridional. Okay, this is called as meridional. MERIDONAL, meridional or MER. Okay, here or FAC. Okay, meridional isomer or facial isomer. Understood? So these are the 2 types, cis isomer and the trans isomer, coming under this category. Okay. And the next one, the last type under 6 coordination is complexes of the type MAA twice A2 N plus or minus. Understood? So in this type, see, this is isomer. Okay. So this is cis and this is trans. Understood? And this is trans. Okay. So in this category, in this type of complexes, the central metal atom M is attached to 2 symmetrical bidentate. So since it is capital A represents bidentate, 2 symmetrical bidentate chelating ligands, okay, AA, and 2 monodentate, small letter represents monodentate, and this capital A represents the chelating bidentate, okay. So two symmetrical bidentate ligands and two monodentate ligands A are present. Okay. So the two letters A and B, A and A in AA indicate the two similar coordinating atoms. Understood? So two similar coordinating. So two similar means this one. So NH2, CH2, CH2, NH2. That is A. Okay. Here also NH2, CH2, CH2, NH2. So that's another A. So two A's are there. Two symmetrical bidentate chelating ligands. Okay. Two bisymmetrical bidentate chelating ligands are there, and then A represents the monodentate ligand. See here, this is Cl. Okay. So in symmetry, in cis isomer, both the monodentate ligands are placed on the adjacent position, whereas in the trans they are in the opposite. They are in the opposite positions. If you see, so the monodentate ligands as well as the chelating bidentate chelating ligands are present in the opposite positions. It's a trans position. So that is trans isomer. Next, we shall see what is optical isomerism. See, optical isomerism is shown by those compounds which possess chirality, that is, which do not possess any element of symmetry. Okay, what you see, when a molecule does not possess any element of symmetry, its mirror image is not superimposable on the molecule itself. Understood? It will not be having a superimposable image. Okay, this makes the molecule more optically active. Such an asymmetrical molecule can exhibit the phenomenon of optical isomerism. Understood? So, when a molecule which does not possess any element of symmetry and its mirror image is not superimposable on the molecule itself, then it is said to be optically active. Such an asymmetric molecule can exhibit the phenomenon of optical isomerism. Okay. So, here also in we have 4 coordination compounds as well as 6 coordination compounds, but 4 coordination compounds does not show optical isomerism, but 6 coordination compounds possess or they show optical isomerism. Okay, so optical isomerism is more common in 6 coordination compounds. Okay, so now we are going to see the optical isomerism in the 6 coordination compounds that are octahedral complexes. Okay, the first type is the complexes of the type M, AA3M. Again, okay, where M represents the central metal atom and AA represents the symmetrical bidentate chelating ligands. Okay, see in this complex, in this type, the symmetrical bidentate chelating ligands AA are coordinated to the central metal atom. Okay, see here I have taken the oxalates. Okay, see to the, let me take and give an example for this category. Cr is the central metal atom, and C2O for oxalate. Okay, so 3 oxalate ions are here. Okay, so this is an example for this category. And see here, this is central metal atom and this is A. Okay, so now see here in this such complexes do not possess any element of symmetry. Okay, and are optically active. Moreover, these complexes can be resolved into optical isomers. Okay, so an example of this category is CrC2O4 3-, and this is optically active. See here in the D form, it can be resolved into D and L form. What is D form? It is dextrorotatory, and the L form is levorotatory. Okay, see here the oxalate ion here we are having, and in this position and in this position. Just to see the mirror image, so just opposite. Okay, so this is D form and this is L form. Understood, students? So this is this compound will be showing optical isomerism. Okay. See the next type, it is complexes of the type MAA twice A2. Okay. See the complexes in which two symmetrical bidentate chelating ligands AA and two monodentate ligands are coordinated to the central metal atom can exhibit this optical isomerism. Okay. So I have given example for this one. See here this D form. Cis can exist in two forms, that is D form and L form. Okay. Whereas this trans form, it is optically inactive, whereas the cis form is optically active. Okay. So here we have two monodentate ligands and two bidentate chelating ligands. Okay. And here it's in the opposite position, right? It's just in the trans form, the chelating ligand as well as the monodentate ligands, they are in the just in the opposite position and they are optically inactive, and it's said to be the trans form. Okay. So example of this type of complex is let me give the example CO Cl2 En twice. Okay, plus or minus. Actually This exhibits both geometrical as well as optical isomerism. Its cis form is unsymmetrical while and the trans form is asymmetrical because it contains plane of symmetry. Hence, the optical isomerism is shown by the cis form only. Okay, optical isomerism is shown by the cis form only. The cis form has been resolved into D form and L form. Understood? Well, fine students, you might have understood the types of stereoisomerism involved in coordination compounds through this video. Let us meet with another important topic in a short while. Until then, it's Dr. Anita Raj signing off from you. Thanks for watching.